Section, we're going to talk about one way to multiply vectors together. The way we're going to mention here is called the dot product. And here's how you do the dot product. Suppose you got yourself two vectors, v1 and v2. You can tell the cat's very excited about the dot product here. And then w, w1, w2. We're going to note the product of v and w with a dot. Hence dot product, v dot w. And here's what we're going to do. We're going to take the corresponding components, so the x components. We'll multiply the x components together. Then we'll take the corresponding y components and multiply them together. And then we'll add their result. Okay? So we're taking a vector times a vector. And what do we get? We get a real number plus a real number. So this gives us a real number. And you may remember when we're talking about vectors and real numbers are also called scalars. So this is sometimes also called the scalar product of two vectors. So for example, we'll take sort of the two vectors we've been working with here, 3, 4, and 1, negative 2. So if I take the vector 3, v3, 4, and the vector w, 1, negative 2, and I calculate v dot w, that's 3, 4 dot 1, negative 2. I multiply the x components together, so 3 times 1. I multiply the y components together, 4 times negative 2, and then I add the results. And so I get 3 minus 8, I get negative 5. So v dot w, these two vectors go in, their product is negative 5, the number negative 5. Now what we're going to be doing here for the rest of the section is trying to figure out what the heck that number means. Why would you even do something like this? What do we get out of the dot product? But first off, let's talk about the properties of the dot product. First off, it's commutative. v dot w equals w dot v. And once again, this is a property that's inherited from the real numbers. So if we go back to the definition here, if we look at w dot v, then that would be w1 v1, w2 v2, add those together. That's the same as v1 w1 plus v2 w2 because of the commutativity of real number multiplication, which gets us back to v dot w. The distributive property, if I take u dot v plus w, I can distribute the u across u dot v plus u dot w. And we have this scalar property. I call this the scalars float. It's a kind of associative property. You can scale a vector v and then dot the result with w. That's going to be the same as multiplying the dot product by the scalar k. That would be the same as scaling w and then dotting it with v. So it's like an associative property, but the scalar just kind of floats to wherever it needs to get to. And then this property, this is a very important property that helps us tie this algebraic maneuver back to something geometric. Okay, so let's actually go ahead and prove this. So what happens if I take v dot v? So I take v dotted with itself, and let's write it out. v1 v2 dot v1 v2. So we're going to take the x components and multiply them together. v1 times v1, the y components v2 times v2, and add them up. That's v1 squared plus v2 squared. Okay. So you square the components and add them up. Now that might sound a bit familiar because the magnitude of v is you square the components, add them together, and then take the square root. So we can see here that if I squared both sides, this then would equal the magnitude of v squared. Okay. These other properties can be verified. We go through some of the details in the book. You're just sort of working through things component by component. These properties, once again, are inherited from the properties we have for real numbers. Okay, -1. Let's prove, or not -1. Example 1. Let's prove this identity. This will be the identity that helps us get into the geometry here from the algebra. So if I look at the length of v minus w squared, that works out to be the length of v squared minus 2 times the dot product of v and w plus the length of w squared. Okay, and what we're going to do is use the properties of dot product here to work this out. So I'm going to start off with the magnitude of v minus w squared. So the magnitude of a vector squared is the same as that vector dotted with itself. And now I'm going to use the definition here of vector subtraction. V minus w is the same as v plus the opposite of w. Right? And now I'm going to use the distributive property. I'm going to distribute the first factor to each of the vectors here in the second factor. So v plus the opposite of w, excuse me here, dotted with v plus v plus the opposite of w dotted with the opposite of w. And then I'm going to use the commutativity of dot product to write the first term here as v dot v plus the opposite of w plus commutativity again, the opposite of w dot v plus the opposite of w. So once again, we're going through this in pedantic detail here, just using the properties that we've established so far. And now we're going to use the distributive property again. Here comes the cat again. So this is going to equal, I've got a v dot v plus a v dot the opposite of w plus the opposite of w dot v plus the opposite of w dot the opposite of w. So v dot v, I know I can replace that with the magnitude of v squared. What can I do with the opposite of v dot the opposite of w? Well, I can remember that the opposite of w is the scalar -1 times w. I'm going to use the commutativity of the dot product and the scalar property to rewrite the opposite of w dot v to be v dot -1 times w. And then I'm going to use the scalar property here to write this as -1w dotted with -1w. And now we're going to continue here. I've got the magnitude of v squared. Now I'm going to use that scalar float property. I'm going to float that -1 out front. So it's going to be plus -1 v dot w. And I'll do the same here. -1 v dot w. And I'll float the scalar out twice here. So I'll have -1 and then -1 times w dot w. And now we're pretty much at the finish line. We're pretty much at the finish line. So, going back to the start here, the magnitude of v minus w squared equals magnitude of v squared. Here I've got -1 v dot w's minus 2 v dot w's. So minus 2 v dot w's. -1 times -1 is +1, and that's the magnitude of w squared. which is exactly what I wanted to show. All right. And so I encourage you to think about this identity you have from algebra, like we did in the last section when we solved an equation. We did the algebra version of it, and then we did the vector version of it. Here we did the vector version of it. Think about when you expand this out. Think about what properties you're actually using to get the left-hand side to work out to be the right-hand side. Okay? Now I know you've got your foiling, right? But foiling is just sort of a shortcut. It's a shortcut way to talk about the distributive property and the commutative property and all that other good stuff. Okay? So there it is. All right, so this identity is going to be key in helping us understand what the dot product is trying to tell us. All right, so to get there, we need to first define something called the angle between two vectors. So if v and w are two non-zero vectors, we can draw v and w with the same initial point. And so we've basically got three cases. Either v and w have the same direction, or they don't, or they have complete opposite directions. And so we're going to define the angle between vectors to always live between 0 and pi, or I guess 0 and 180 degrees. Okay. And so here's the geometric interpretation of the dot product. It turns out that v dot w is the length of v times the length of w times the cosine of the angle between them. Okay, so how are we going to do such a thing? Okay, well, we're going to go back to our little diagram here. V, W, and then V minus W. So this was the vector diagram we had. There's the angle between them. And now I can just look at the lengths of these things. And make a triangle. And there's my angle theta. That's between V and W. And now I can hit this with our law of cosines. So here comes the law of cosines again. So law of cosine says, if I look at the length of V minus W squared, that's the sum of the lengths of the other two sides. Minus 2 times the product of the lengths of those sides times the cosine of theta. And now, I think you might see what's going on. Now I'm going to hit this with example 1. Example 1 says that this is also equal to the length of v squared plus the length of w squared minus 2 v dot w. And now we can see what's going to happen. These would drop out. We'd be able to divide by -2. Boom, we get our result. Okay. Now, because the angle between two vectors is defined to be between 0 and pi, we can solve this equation for cosine of theta, v dot w over length of v, length of w, and then we can take the arc cosine of both sides to actually get what theta is. So if you want to, once again, it depends on how much stuff you want to remember. Theta would actually be the arc cosine of v dot w over length of v, length of w. Right? So that's how you can get the angle between two vectors in one fell swoop. I do want to make a note about this, and we'll talk more about this here in just a bit. But if you remember back to the last section, we defined v hat to be v over the length of v w hat to be w divided by the length of w. And I can use properties of the dot product here. Because if I write out really what this means, I've got 1 over the length of v, 1 over the length of w, times the dot product v dot w. So I can float the 1 over length of w scalar to go with the vector w, and I can float the 1 over length of v scalar to go with the v. And so I can actually rewrite this as the length, or v over the length of v dot w over the length of w, which would be v hat dot w hat. So this is another way we can try to get at what the dot product is doing. If I take the dot product of the direction of v and w, that's the cosine of theta. So that's another way you can think about the angle between the vectors if you want. Oops, looks like I adjusted the thickness here. Oops, let's bring it back. Theta is the arc cosine of v hat dot w hat. That's an alternative way to write it. Example 2, find the angle between the following pairs of vectors. Graph each pair of vectors in standard position to check the reasonableness of your answer. Okay, so to get the angle between two vectors, I need 3 things. I need the dot product and then the magnitude of each of the vectors. So let's start off with, we got v here is 3 comma negative 3 square root of 3. And we got w negative root 3 comma 1. So here comes v dot w. Multiply the x components together, negative 3 square root of 3. Multiply the y components together, negative 3 square root of 3. And add the results, I get negative 6 square root of 3. To get the magnitude of v, I square the components, add them up, take the square root. So 3 squared plus negative 3 square root 3 squared. 3 squared is 9. Square negative 3, you get 9. The square root of 3 squared is 3, so that'd be 9 plus 27. That gives us the square root of 36, which is 6. The magnitude of w, the square root of negative square root 3 squared plus 1 squared. This is the square root of 4, which is 2. And so the angle between the vectors theta is the arc cosine of v dot w, negative 6 square root of 3 over magnitude of v times magnitude of w over 12. So this is the arc cosine of negative root 3 over 2. And that's one of our common angles. So the negative means we're in quadrant 2. The reference angle would be pi over 6, so this would give us 5 pi over 6, or if we're working in degrees, that would be what, 150 degrees? Okay, so how can we graph these to see how reasonable they are? Well, remember, if we plot v and w in standard position, then the terminal points are, the coordinates of the terminal points match the components. So let's go ahead and fire up Desmos here. And let's just plot the point 3 comma negative 3 square root of 3. Comma. There we go. Boom. So we'll label that. Okay, we'll just label that v. All right, and then we'll do the same for w here, negative square root of 3 comma 1. We'll label that w. All right. So the vector v would start at the in standard position. We start at the origin, and we head down to v. The vector w, we'd start at the origin and head over to this point here. And we're saying that the angle between these two things is 5 pi over 6 or 150 degrees, right? Certainly seems reasonable. Okay, certainly seems reasonable. All right, let's take a look at number 2. We've got 2 more pairs here. We've got V is 2, comma 2. W is 5, comma negative 5. So let's go V dot W. Once again, we multiply the corresponding components. So 2 times 5 and add the results. And to your surprise and or delight, this works out to be 0. So it really doesn't matter what the length of V or the length of W works out to be. V and W are non-zero vectors, so they'll have non-zero lengths. We're going to have 0 in the numerator here, and we'll end up with some non-zero number in the denominator. So we just get the arc cosine of 0, which is pi over 2, aka 90 degrees. So that means that we should have a right angle between V and W. So let's fire up Desmos and see if that seems to make sense. So V is 2, 2. W is 5, negative 5. So we'll put V here as 2, 2. And then W as 5, negative 5. So once again, we're thinking of these vectors in standard position. So that would be the vector V. This would be the vector W, and by golly, that certainly looks like a 90-degree angle. Right. Last but not least, we've got V is 3, negative 4, and W is 2, 1. So V is 3, negative 4, and W is 2, 1. Okay. So let's take V dot W. Once again, multiply the corresponding components and add the results. So here we get 6 minus 4, which is 2. The length of V, square the components, add them up, take the square root. Magnitude of W, square the components, add them up, take the square root. So we get the length of V is 5, the length of W is root 5. So theta here would be the arc cosine of V dot W2 divided by 5 square root of 5. And that's, as far as exact answer, that would be the exact answer. Let's approximate this. And we'll approximate it with degrees since we're a little more comfortable with that. So go to degrees here. Arc cosine 2 over 5 square root 5. So that's roughly 80 degrees. So let's check here. 3, negative 4. 2, 1. Starting once again at the origin, putting these vectors in standard position. Yeah, it's believable that that's 80 degrees. All right, it looks close to being a right angle. Okay. All right, so we're getting closer to understanding what exactly the dot product's doing for us. So if we think about this formula, once again, we're assuming v and w are non-zero vectors so that their lengths are, so we're not dividing by 0. If v dot w is a positive number, right? So let's see, the denominator here, this is always going to be a positive number. So if the numerator is a positive number, it means the cosine is positive. That gives us a quadrant one angle. So we're in this first situation here. So v dot w is positive. That tells us theta is acute. That means that v and w, they're not going necessarily in the same direction, but they're going sort of in the same direction. If v dot w is 0, then that's going to zero out what we have here, and that's going to produce a 90-degree angle. Right? Vectors that are at a 90-degree angle are called orthogonal. So it's that ortho prefix. You'll see ortho, like orthopedic, ortho configurations in organic chemistry. That typically corresponds to the notion of proper or right 90 degrees. All right? So lines that intersect at 90 degrees are called perpendicular lines. Vectors that are 90 degrees to each other are called orthogonal vectors. So the dot product being 0 is going to tell you the vectors are orthogonal, and vice versa. If the vectors are orthogonal, the dot product is 0. And last but not least, if your dot product is negative, then that means your arc cosine is going to throw you into quadrant 2, and that means the angle between the two vectors is obtuse. Right? So this is kind of a big deal. Once again, depending on where you go from here, the dot product detects orthogonality. For two non-zero vectors, v is orthogonal to w if and only if v dot w is 0. So you might have seen this notation before for perpendicular lines, same for orthogonal vectors. So this t, upside down t here, means orthogonal. So if the dot product is 0, that means the angle between the vectors is 90 degrees. They're orthogonal, and then vice versa. Okay. So as an example of this, you can prove this relationship between lines. If you have two lines, you can prove the lines are perpendicular if and only if the product of the slopes is -1. All right, so how can we get this involved? So let's just do a little sketch here. Here's L1, y equals m1x plus b1, and then here's L2, y equals m2x plus b2. We want to show that they're perpendicular if and only if the products of the slopes are 0. So what we can do is we can actually just pick a couple of vectors that would be parallel to the line. So let's pick a vector here. Doesn't matter where we start. We can start here. And let's call this v1. And let's think about what the slope means. So remember that m1, that would be the change in x over the change in y. So the change in the x's on that line over the change in the y's on that line. I can think of that as a ratio of m1. I'm sorry, it's upside down. It's change in y over change in x, excuse me. Change in the y's over the change in the x's. That's got the ratio of m1 over 1. So if I wanted to find a vector, I could pick my delta x1 to be 1 and my delta y1 to be m1. So I could pick the vector v1 to be 1 comma m1. So for every 1 unit I go over on L1, I'm going up m1 units. And likewise, I could do the same thing here with L2. For every 1 unit I go over in the x on L2, I'm going to go up m2 units. So L1 being orthogonal or perpendicular to L2 would be the same as the vector v1 being perpendicular, or orthogonal rather, to v2. And this is the same as v1 dot v2 being 0. So the dot product detects orthogonality. So let's see what that would be. if I multiply here the x coordinates, the x components, 1 times 1 is 1. The y components, m1 times m2. So m1 times m2 plus 1 is 0. By golly, that means that m1 times m2 has got to be negative 1. So everything old is new again. All right, we have this new idea of orthogonal vectors, and that reduces to the same idea we had of perpendicular lines. Okay, now it's time to really get to what the dot product does. And this is the concept of vector projections. So once again, let's assume that we've got two non-zero vectors, and we'll put them at a common initial point. Could be the origin, really doesn't matter. What we're going to do is we're going to project V down to W. So if we think of shining a light here above V at a right angle, this projection here, P, think of this as the shadow of V along W. Right? So this is trying to see how much of this V would be in W's direction. That's called the projection P. So the projection P is short for projection of the vector V onto the vector W. All right? So think of that as like the shadow of V along W. All right? I want to figure out a formula for P. So like every vector, P is the product of its magnitude times its direction. All right? Now there's a couple different cases here. The case that we've sketched here, we've got an acute angle theta. All right, so we're going to assume that, theta, the angle between V and W, we're going to assume that theta is acute here. So it's between 0 and pi over 2 radians, 0, 90 degrees. So we're going to assume that theta is acute, and then you can look in the book to see how we can adjust things for the other method. So if theta is an acute angle, then when I project this down, the direction of P is the same as the direction of W. All right? So in this particular case, P hat is the same as W hat. So now I just have to figure out the magnitude of P. Okay? So how much of that is there. So to do that, I can set up this little triangle, little right triangle here. I got the magnitude of V, the magnitude of P, and I've got theta, the angle between V and W. And so I can set this up that the cosine of theta would be the length of the adjacent side over the length of the hypotenuse. That would be the magnitude of P over the magnitude of V. And so the magnitude of P would be the magnitude of V times the cosine of theta. But I know a formula for the cosine of theta. I know that the cosine of theta is V dot W over the length of V times the length of W. So this is how we're getting the dot product involved here. So I can see that the magnitude of V would cancel out, and I get the magnitude of P is V dot W over the length of W. All right. Now I'm all set to figure out the vector P. So P equals the magnitude of P times the direction of P. The magnitude of P is V dot W over the length of W. In the scenario we're in, where theta is an acute angle, P hat's the same as W hat. And so at this point, I can take things in a couple different directions to get two different formulas for P. The first formula is going to be the one that's probably easier to calculate. So to get the first formula, I'll substitute in W hat. as 1 over the length of W times W. And so one formula we get for the projection is V dot W over the magnitude of W squared times W. Okay? So that's formula 1. V dot W over the magnitude of W squared times W. We can rewrite this using properties of the dot product because the magnitude of W squared, that's the same as W dot W, right? And this is usually a fan favorite because it involves dot products, which are pretty easy to calculate. And it kind of looks like what we have here is we've got like this sort of fractional part, V dot W over W dot W times W. So it's important to understand that this here is a real number. All right? This is giving us sort of a fraction of how much of V is in W's direction, or how much of V is compared to W, and then we're multiplying that by the vector W. So this is really calculating how many W's the projection P is. All right, P is this fraction of W's. All right. Another way we can take this is V dot W is a scalar. Excuse me, V dot W, I can rewrite this and float that magnitude of W up with the vector W like we did before. And that's called W hat. And so the second formula we get, which theoretically kind of tells us what's going on here, P is V dot W hat times W hat. And so this is what we can think of, is when you take V dot W hat, this is telling us how much of V is in W's direction. We find out how much of V is in W's direction and then multiply it by the direction of W, and that's where we get our projection. Okay? And so this really is what the dot product is doing. If you take a vector dotted with a unit vector, this gives you how much of that vector is in that direction. And this how much is a signed thing, plus, minus, or it could be 0. If the dot product is 0, then that means that none of the vector is in that direction. If it's positive, that means that some of the vector is in that direction. If it's negative, then it means that the vector is going in the opposite direction. Okay. All right, so here's these formulas. Once again, this seems to be the fan favorite because it's all dot products. But this kind of tells us theoretically more what's going on. Okay. So to kind of go back to my last comment there, you know, if we go back to these 3 cases, and I think about projections here, V dot W is positive. Notice that the projection vector here is going to have the same direction as W. Notice what happens if I try to project here. You get nothing, right? If I shine the light straight down, I get nothing. So the dot product is 0. My projection vector here would be the 0 vector. And if I shone the light down here, notice what happens is the dot product is negative. Instead of being in the direction of W, we would have the projection going this way, which is in the opposite direction of W. Okay, so that's why it's sort of this signed quantity of how much of V is in W's direction, plus, minus, or 0. I'll put all this together here for us. So we got vector V, vector W. we're asked to find the projection of V on the W and then check the answers geometrically. All right. So, projection P, take V dot W over W dot W times W. So we're going to see how many W's the projection is going to be. So we get V dot W, multiply the X components together, 1 times negative 1, and then add to it what we get when we multiply the Y's together, 8 times 2. So minus 1 plus 16, that's 15. W dot W, square the components and add them up. Negative 1 squared is 1, 2 squared is 4, so we get 5. So we get 15 over 5 W's, which would be 3 W's, which would be the vector negative 3, 6. Okay. So let's go over to Desmos and we'll plot the terminal points and see if we can get this to make sense. All right, so V is, we put V in standard position, the terminal point would be 1, 8. I'm going to call that V. I think we were using that as green. Negative 1, 2. I'm going to call that W. Whoops. And then we had what? Negative 3, 6. That was our P. Okay. Let's see if this makes sense here. Zoom in a little bit, perhaps. All right. So the vector V, so going from the origin out here, so in standard position, I start here at the origin, and I go up. There's my vector V. Starting at the origin, heading up, that's my vector W. And then if I project this down onto W, I should get P. And we found P to be 3 W's. So if I take W 3 times, I should be able to get to P. So W, because of the scale here, W is what? Counting blocks, it's 2 of these blocks over, 4 blocks up, right? So negative 1, 2. So here's W, 1 W, 2 blocks over, 4 blocks up. And then that'd be another W. And then 2 blocks over, 4 blocks up. Boom. There's another W. Okay? All right, so the projection is 3 W's. Now, how could I check it, though? Because if it really is the orthogonal projection, I should have a right angle there. All right? What I'm going to do is I'm going to call this vector Q. So Q is going to be the vector that starts at the terminal point of P and ends at the terminal point of V. In other words, I'm going to define Q so that the vector P, or excuse me, the vector V is equal to the vector P, so going along in the direction of W. So I'm going to go 3 W's and then I'm going to go Q. So I'm going to define Q so that it's what's left over. In other words, Q is V minus P. All right. And if this really is the orthogonal projection, Q and W should be orthogonal. All right, so let's check that out. So what would Q be in this case? Q is V minus P. V was 1, 8. P was negative 3, 6. The way we subtract vectors is we subtract corresponding components. So be careful here. 1 minus a negative 3. 8 minus 6. This is the vector 4, comma 2. So that's my Q. And now let's check. Is Q orthogonal to W? Well, let's take the dot product. Q dot W. W was negative 1, 2. Multiply the x components together, minus 4. Multiply the y components together, 4. Add them up, and guess what we get, folks? 0. So that actually proves that Q is orthogonal to W, which proves that P really is this orthogonal projection, right? So basically V, and in more fancier math classes, they put like a little dot over this. V is this direct sum of P and Q, meaning V is P plus Q. P is parallel to W, so P is parallel to W, and Q is orthogonal to W. And this is the generalized decomposition theorem. So V and W are non-zero vectors. There are unique vectors, P and Q. So that V equals P plus Q, where P is parallel to W. In other words, P and W are off by a scalar, and Q is orthogonal to W. So that, and you see this kind of thing happening like in your physics class all the time. Anytime you have a vector V and a vector W, you can always decompose V. You can always decompose V. I'll make W. And that W's are going to be looking like the projections. There we go. Go this way. So you can always decompose V into two vectors, a vector P and a vector Q, where P and Q are orthogonal. P is parallel to W, Q is orthogonal to W. Okay? This is very much like the decomposition we had with I and J. If you remember I and J, right, we had V was V1I hat plus V2J hat. This is basically saying we can create our own little I's and J's no matter where we are in space. We don't need to be sort of tethered to the origin there. We can kind of break things up. So like in physics, the classic, you've got this, something on an inclined plane, and they talk about this so-called normal force acting on it. Okay, so that's normal to this plane. All right, so that's like you're breaking things up. You've got two forces, right? They're at this angle here. All right, so that's a big deal, right? And when you get into calculus, you can generalize these sorts of things. You throw some linear algebra in there. This kind of decomposition theorem helps you do, of all things, signal analysis, breaking down a sound wave into its frequencies, and then reconstructing the sound waves from its frequencies. Okay, so it's pretty sophisticated stuff. Anyhow, about the section talking about a physics quantity called work. Work is, its most basic form, work is force through a distance. Okay, the basic equation of work is force times distance. So for example, let's say you were lifting a book. So you got your 5-pound book, and you're lifting it, let's say 3 feet off the ground. Then the work being done would be those 5 pounds times your 3 feet. That would be 15 foot-pounds. So foot-pounds is a unit of work. If you're using the other system, Newton meters, which are joules. Now you might say, well, you're working against gravity. Since you're going up, gravity's pulling down. So depending on the convention, the actual number you record may be negative 15 foot-pounds because we're working against the system. So it all depends on how you set things up. In general, though, the force acting on the object may not be in the direction of or completely opposite of the motion. So suppose we've got an object here at point P, and we're trying to move it to point Q by tugging on it at the force F. All right. The thing is, the only part of this force that's going to help you accomplish this motion is how much of F is in the PQ direction. Okay. So once again, work is force times distance. The force here that's going to be moving the object is how much of the force F is in the direction of PQ. And this is exactly what the dot product does to help us. So this would be the vector F dot the direction PQ. The distance we're traveling would be the magnitude of PQ. Right. Now, the magnitude of PQ is a scalar. I can float that scalar and associate it with either factor here. So what I can do is I can rewrite this as F dot the magnitude of PQ times the direction of PQ. And that's exactly the vector PQ because it's its magnitude times its direction. So I get F dot PQ. All right. So this is how we can generalize work when forces are acting and when forces are not acting directly in the direction of motion. It's F dot PQ. So W equals F dot PQ. Now, when you take physics, right, you could break this up using our formula here. Magnitude of F, magnitude of PQ times the cosine of the angle between them. Right, so that's another way you may see this in your physics class. All right. All right, so example, is that really? Yeah, example 5. Taylor's pulling her wagon here, exerting a force of 10 pounds to pull her wagon a distance of 50 feet over level ground. The handle of the wagon makes a 30-degree angle with the horizontal. How much work did Taylor do pulling the wagon? Assume the force of 10 pounds is exerted at a 30-degree angle for the duration of the 50 feet. Okay? So, work is F dot PQ. So we can get the force here. We can look at the components here. That force, the force exerted is a force of 10 pounds. So that's the magnitude of the force times its direction. So that's 10 pounds. And the angle here is 30 degrees. So I've got 10 cosine of 30 degrees, 10 sine of 30 degrees, 5 square root of 3, comma 5. So that's the force. Now as far as PQ, it goes 50 feet. So I guess I can just start this here at 0, 0. And then if I go 50 feet, I can take PQ to be the vector 50, 0. Because we're going across level ground. So if I go about it with this formulation, oops, that's PQ down there. I just have to multiply the x coordinates together. So 50 times 5 root 3, that's 250 root 3. 0 times 5 is 0, so it'd be 250 root 3 foot-pounds of work. So that's how you can go about it if you want to model it as a dot product. Or you could look at magnitude of F, magnitude of PQ, times the cosine of the angle between them. It's 10 pounds over 50 feet. Once again, times the cosine of 30 degrees. Cosine of 30 degrees, that's root 3 over 2. You'd have 500 divided by 2. In other words, 250 square root of 3 foot-pounds. You get to the same answer. Okay? So that'll do it for the dot product. Once again, if you're going on in math and engineering, you will see this concept of vector decomposition and orthogonality get generalized to amazing effect. All right? The whole concept of getting an MRI to non-invasive imaging of what's going on inside your body, that all comes back to the principles that we put down here way back in section 12.4 of trigonometry.